Kafka is designed as a distributed system that spreads data across multiple brokers, ensuring high availability and fault tolerance. In its architecture, we have producers, brokers, and consumers. Each plays a key role in handling the massive amount of data Kafka is built for. Let's visualize the basic components of Kafka architecture with a diagram. Now looking at this diagram, you can see that Kafka's producer sends data to brokers, which then replicate the data to other brokers. This replication is crucial for fault tolerance, ensuring that if one broker goes down, others can still provide access to the data. Kafka brokers are the core of each distributed system. Each broker is responsible for managing partitions of topics, ensuring redundancy and fault tolerance across the system. Let's visualize three Kafka brokers and two topics, each of which has only one partition first before we dig deeper into partition details. In this diagram, we can see a Kafka cluster made up of three brokers. Broker 1 handles the purchases topic as its leader, while broker 2 is the leader for the notifications topic. Broker 3 doesn't manage any partitions in this setup. Zookeeper coordinates the cluster and ensures smooth broker operation. On the right, we have the purchases domain where producer consumers send receive data to the purchases leader on broker 1. On the left, in the notifications domain, producer consumers send receive data from the notification leader on broker 2. This architecture shows how Kafka partitions data and balances roles across brokers for topics with only one partition. Kafka divides topics into partitions to achieve parallelism and scalability. Each partition in a topic is assigned a leader broker that handles on the read and write requests. Meanwhile, follower brokers replicate the leader data, providing redundancy and ensuring high availability in case of a failure. This partitioning allows Kafka to handle massive amounts of data efficiently by distributing both the load and processing tasks across multiple brokers. In our example, we can illustrate a purchases topic that is split into two partitions. Partition 0 handles purchases from user with odd numbers, while partition 1 manages purchases from users with even numbers. By doing so, Kafka maintains the order of data within each partition, while spreading the workload across multiple brokers. This architecture ensures Kafka's performance scales with the number of brokers and partitions, allowing it to process data concurrently. Now let's explore Kafka topics with multiple partitions using the same example. I assume only two partitions for the purchases topic for simplicity. The same concept applies with a number of partitions. Now the purchases topic are managed across the two broker 1 and broker 2. The topic is divided into two partitions, and for each partition, there's one leader broker and several followers for redundancy. In this graph, we are focusing on partition 2. Partition 2 leader resides on broker 2, while the follower is hosted on broker 1. Data flows to and from these brokers through producers and consumers in the purchases domain. When a producer sends data, it first reaches the partition 2 leader on broker 2, ensuring high availability. The follower on broker 1 passively replicates the data to maintain consistency and fault tolerance. Both the producer's data write and the consumer data read to partition 2 are highlighted in red to emphasize the critical flow for this partition. In this setup, the producer sends data to the leader of partition 1, which is on broker 1. The leader replicates the data to its followers, which is broker 2. Consumers can only read from the leader, ensuring consistency in data access. To ensure data durability, Kafka uses replication. Each partition's leader replicates the data to its followers, which can take over if the leader fails. This is how Kafka achieves fault tolerance. Let's visualize the failover process when a leader goes down. In this scenario, broker 1 is active, serving as the leader for partition 1. However, broker 2 has a follower for partition 1, which ensures redundancy and fault tolerance. When the producer sends data to partition 1, it communicates with the leader on broker 1, while the consumer reads from the same leader. Meanwhile, broker 2 is prepared to take over as the leader if broker 1 fails. When broker 1 goes down, Kafka automatically promotes the follower for partition 1 on broker 2 to be the new leader. Both the producer and consumer now interact with partition 1's new leader on broker 2, ensuring continuity.